There we go. All right. Well, I'm really almost done with your tests. I've got a couple of scratch work I have to get through for a couple of you, but that really should be available hopefully not long after our meeting here today, our class here today, and you can check those out. So I'm going to say it looks like everybody's passed so far, so that's a good sign if nothing else, right? All right, well, here we are. We're going on to chapter 4, and all right, the linear equations. I forget what the exact title. Dealing with linear equations in 2 variables. Here we go. One more person. There we go. Yeah. Linear equations in 2 variables. We actually have seen a few of these equation shapes already, and we've tried to come up with ways to sort of express one thing in terms of the other. So there's only ever one variable. One type, I'll mention that you just worked with on your test, the typical form that we're going to see for this kind of situation or equation with 2 different variables in it. And Mom kind of wanted you to write this equation for this formula a certain way. And one of you in particular wrote it, kind of like did all the calculation already, and then you entered it into Mom, and it didn't like it. Well, I give you credit for that. You know, I understand, but maybe you'll recognize that when you get there. So here is that kind of situation. I usually start off with something like your repairman. Maybe a plumber's coming to your home to do some work, and they charge, just to show up, an $80 fee. So here's a fixed amount, right? Whether they do anything, they're going to just, the fact that they showed up, they're going to charge you this much. And then maybe, I have no idea what they're going for these days, then another $40 for every hour that they actually work. Now, maybe, you know, problem like this, reality might be a little more complicated, parts and stuff like that. But then, how can we write an equation that would describe the cost of this plumber working for us when I don't quite know yet how many hours that person is going to work? So I might say the cost, well, I know it's going to be $40 for every hour that person works, plus the fixed fee, $80 just for showing up. So here I use C for cost. I could have put H in for the number of hours, I guess. In a word problem like this, you might see letters for variables that represent concepts in the problem. But here now I have a relationship that I can use no matter how many hours this person works. If it's 1 hour, it's going to be 40 plus 80 is my total cost. If it's 2 hours, it's going to be 80 plus 80. 160 would be my total cost. So these actually are 2 different variables, and my final value depends on whatever value I put in for this other variable. Now, we've seen a couple like this, like the one I was mentioning on the test, that said, well, if your total cost was $200, how many hours did that plumber work? We'll get there eventually, right? We're going to see some more like this. So you knew the final value. It wasn't an equation with 2 variables to start with. You were given that final value, and then the idea was for you to write this equation and then manipulate it and figure out how many hours that means that person must have worked for you. Now, as I suggested, somebody already kind of did the calculation. Oh, they knew that it was going to be subtract the 80, right, and then divide by 40, and that was going to get you the X. That's totally true. You're just kind of doing the calculations ahead of time. But notice that depended on you knowing already the final value, so you could kind of claimed that this was the equation. That's an equation, that's legit. And I've actually complained in the past about that problem. And Mom, you know, is there a way we can get it to accept this answer? And different folks have weighed in differently. Oh, I really think they should write it this way. Well, we haven't taught it that way yet, really. Don't worry about that. Anyway, if you recognize that shape, or something you did on your test, I went in and gave you credit for it, even though Mom didn't originally. But this now represents an equation, has two different variables, and it describes their final cost in terms of hours, how many hours. And you could, what you want to think about right now is there's an infinite number of possible solutions, right? Well, a person's not going to work forever, but if it's 1 hour, it's one price. If it's 2 hours, it's another price. If it's 3.5, it's another price. Any number I can put in there for X is going to give me a value, a corresponding cost value. So we have two different numbers that will always go together in these situations. All right, so that was sort of framing the situation here, getting this started. And, all right, well, sorry I didn't really mention it earlier. If you've got some graph paper around, that's going to be handy for the next few lessons in particular. If you want to go to the math department website, you know, RCC math department, put it in the search, whatever. Down near the bottom of that website page is a link to a free graph paper site. You can probably Google it yourself, but free graph paper. You can print out graph paper, something like that. I had a bunch and I was going to post them and I somehow lost them. So anyway, but I'm going to be working off my whiteboard here and drawing graph paper, you might say. Okay, well, so you might have to do the same here for a while. We've already been doing some graphing in one dimension using our number line, all right? And if I wanted to identify the single solution to an equation that we've been working with, you know, if X equals 3, right? 1, 2, 3. I could just put that dot there, and there I've actually graphed the solution. When we were working with the inequalities, there was a whole interval of solutions, and we actually shaded in one side of the number line to show all the possible solutions to that situation. Well, if I've got one number for 3 that I'm putting into, say, my plumber example, I'm going to get a cost value that comes out that goes with it. So I've got 2 numbers that go together. So I need a second dimension, my axes, right? And so we draw a second axis perpendicular to that one. And neaten this up a little bit, all right? Go from there again. So I've got one axis that I can use to represent one of the values. Let's say in my plumber exercise example, the hours might be my x-axis, or t for time or something. That's another common one. And the resulting output or cost, that would have been what I might label the vertical axis, C, you know, giving a name to the axis. Now, in our abstract problems that we're going to work with, we usually work with X and Y. So we label these axes. So I'm talking about some conventions now, things that you should always try to remember to do if you were actually ever drawing your own axes on paper and, you know, having to turn this in. So we label our axes, right? So for a certain X value, I get a certain Y value. And when I put them together, that's going to give me a point out here in 2 dimensions out of the plane. All right. Units. Now, you're going to get away with Mom kind of providing units for you I usually got to the point where I said, well, if you don't write something, I'm going to assume they're all ones. 1, 2, 3, 4, 5. 1 unit between each line. But it's kind of nice to just put some representative on your own graph, representative unit on each axis. And then we can count from there. Well, if each one of those is 1, 1, 2, 3, I can count, figure out where we are. Depending on the context of a problem you might be working with, maybe this axis does represent hours, right? 1, 2, 3, 4 hours, but maybe the cost you want in terms of bigger units, like, oh, I'm going to get to $100 really quick. So maybe each one of those lines was 50. So within an axis, the unit size has to stay consistent. I can't go 1, 2, 5, 20, something like that. But the two axes don't have to have the same units. Think of like graphs you might have seen of number of years and then the total cost of some, whatever, debt or something like that. Definitely different units. So that's why, especially in a word problem, you want to identify your unit size on your axes. But if we're just working with 1s and 2s and so on, we can call them 1s and count from there. All right? Units on your axes. Notice that divides our plane, right? Without these, where am I? Divides our plane into what we call 4 quadrants. And the convention is to just label them with Roman numerals starting up here, it's quadrant 1, and going counterclockwise. You'll have a mom question. Here's a point in the plane, which quadrant is it in? Answering the question. All right. Then, now this point right here, right, it was 0 in the x direction and 0 in the y direction. We call it the origin. It's where we start, origin. All right. And every position in the plane, right, has an x value that corresponds to it and a y value that corresponds to it. How far have we traveled in the x direction, positive or negative? And how far have we traveled in the y direction, positive or negative? Convention, up is positive, down is negative, all right? That same x-axis we've always worked with, positive, negative, right? -1, -2, and so on. So the origin is the point where my x value is 0 and my y value is 0. Here we are, we're using parentheses again and a comma. This is called an ordered pair. And the first, ordered because they're in order, right? The first value is always your x value, and the second value is always your y value. They're in order. If you get them mixed up, you're going to mess up. All right, so the origin is the point 0, 0. All right, going from there. And now notice any point I would have out here, right, in that quadrant, right? Let's say I went over, looks like I went over about 3 and I went up 4. I have an x value of 3, just making something up, right? X value of 3, 1, 2, 3, 4, y value of 4. There are the coordinates for that point. I just put in that plane. Yeah. Okay. Well, because I was in that first quadrant, right? All the x's are positive and all the y's are positive. So we just talk about the fact that both signs are positive in the first quadrant. If I had a point back here, well, let's see, 1, 2, 3, 4, -4 in the x direction, and 1, 2, 3, let's say I went up 3, positive 3y, right? Negative x, but positive y. The signs in that second quadrant will always be negative for the x value, right, and positive for the y. When we're in the third quadrant, we're negative x and negative y. Right, going to sleep, haha. And in the fourth quadrant, positive x, but negative y. So just understanding the signs in the different quadrants. All right, so if I have a point in the plane someplace, then I want to be able to count the squares and come up with its coordinates. So there, I just plugged one in there. You can make one up for yourself. Doesn't look too bad on the screen there. So what are the coordinates for that point? Starting from the origin, in the x direction, I went positive 1, 2, 3. Starting from the origin in the y direction, I tried to make that look like I went down 1, negative 1. So just being able to count and watch the units in a problem, count the squares and find the coordinates of points in the plane. See what if I did something down here, squeeze one in there. Looks like I went 1, 2, negative 2 for my x. And 1, 2, 3, 4, I say went down to negative 5 for my y. So there are the coordinates. The ordered pair the x, y values for that point in the plane. And just a couple special ones, I guess we talk about. The ones that are on the axes, right? If it's on the axis, one of the values is 0. If I've got a point here, I have moved, looks like negative 4 in the x direction, but I haven't gone up or down. So my y value is 0. I try to drill in, make the point that if you're on the axis, a certain axis, the other value is always the 0. I'm on the x-axis, that means y is going to be 0. If I'm on the y-axis, means I haven't gone left or right. My x value is 0. 1, 2, 3, 4, 5. Squeezing a lot in on this first one. Just lots of information here. Okay. Clear and try to save my grid as much as possible right now. I don't have to draw it a million times. I'm working on a plastic template I can put up here and have a grid on it permanently. Didn't get it done yet. Oh. All right, so let's say I've still got these ones. You'll be asked then to plot points yourself. And mom, they've got that little pencil tool, you know, you go put a dot in the plane there someplace, right? So let's say I want to find the point 5, negative 3. Can you put that on the graph yourself? Or let's say negative 2, 4. Can I put that on the graph myself? Well, it means 5 in the x direction, positive, and 3, negative y. So 5 in the x direction, 1, 2, 3, 4, 5 means I got out this far. Negative 3y, 1, 2, 3, went down that far. So you don't have to put in those little dots, but I'm just trying to show where those two met. That's where that point goes, out there in the plane. Let's see, negative 2 in the x direction, and 4 to the y direction, positive 1, 2, 3, 4. Right about there. Locating those points in the plane. Okay. Hoping that makes sense. So far, so good. Clean this up a little bit. All right. A linear equation in 2 variables. That's what these are called. Linear equation. Here's my abbreviation, EQN. In 2 variables. There are going to be 2 variables in these equations. One form we've actually seen when we were manipulating formulas. Now, the y and the x are the variables that'll be in these problems M and B are going to be numbers, and they mean things. We'll get there eventually. Right? So there's one typical form for a linear equation. We're getting to, well, why is it a linear equation, right? And let's see, the other shape kind of has everything over on one side equaling a final number. Again, we already tried to practice working with that equation a little bit ourselves in the previous sections, manipulating that like a formula. Again, the X and the Y here are going to be the variables, and the A, B, and C are going to be numbers that describe that relationship between them. So if I have an equation like this, one of these shapes, let's say here is such an equation. And somehow or other, this final value, whatever it stands for, is a result of multiplying whatever input, whatever number I would put in for X, I multiply by -2, and then I add 7. So I do my work over here. Depending on whatever X I put in, I'm going to get a certain output Y. And if I put in a different X, I'm going to get a different output Y. Right? So we get two different numbers that always work together in these problems. So what are we going to try to do? Well, first we're going to test to see if certain values are solutions or not. I should have turned my page sooner so that I got to my examples where I know what it's going to, how it's going to work. All right. Allow me to do a little eraser math here. I'm going to change that to a 6 just because I've got examples in my notes here already. All right. Sorry. Fix that for yourself. So we'll be asked to verify whether a certain XY pair is a solution. If I put in 3 for X and 0 for Y, is it true? That's what we're asking. If I plug in these two numbers for the X and the Y, does it result in a true statement? That makes this, if it is true, that makes this combination, right? This combination of X's and Y's a solution to this equation with two variables. Every solution now has to have two numbers that go together. If X is this, the Y's got to be that, or vice versa. So plugging them in, if I put in a 0 for Y, -2 times the 3, is it true? Do the calculation. Yes, it's true. So yes, that one's a solution. Test another one. How about 1, 4? If I put in that one, is it true? All right, if I put in that point, I put in a, no, it's kind of unfortunate. I have to go make sure I get the second one for the Y value, right? And then -2 times a 1 plus 6. All right, 4 equals -2 plus 6, 4 equals 4. Oh, yeah, that one's true also. I found two different solutions to that equation. So what do I usually do? I have to make up something where it's not going to work, right? Maybe it's real boring. -2, the Y value, is -2 times -2 plus 6. Is that true? So, right, there's the X -2 and the Y -2. And that's going to be what? +4 plus 6. -2 is not equal to 10. So that one was not a solution to that particular equation that I started with. All right. How about one of these over here? Same idea. There is an equation that is in that shape. It has two variables, X's and Y's. These numbers are set, so the relationship between the X and Y is always the same, even in this one, right? The relationship, what do I do to X after I put in a number? and then get my output y. It's always times -2 plus 6. Over here, I'm going to plug in some points. How about if I try 3, 0 here? I put in 3 for x and 0 for y. Whoops. Look at getting ahead, Steve. Oh, yeah. 2 times the 3 plus 3 times the 0. Does that equal 6? Yeah, I'm going to get 6 plus 0. 6 equals 6. Yep, that one's a solution. How about, say a 2, 1. If I put in a 2 for x, 2 times 2 plus 3 times 1, does that equal 6? 4 plus 3, nope, that one's not a solution. So just plug in the numbers in carefully, x for x, y for y, and testing to see or verify whether or not that point is a solution to that equation. Notice that was just totally doing calculations, didn't do anything with the graph there. Yeah. And then they'll throw some at you where they're presenting a table of values. These usually look something like that. Maybe they're called T-charts sometimes, but you know, a column for all your x values and a column for all your y values. These are going to start out by giving you some numbers to plug in for one of the values and find the value, calculate the corresponding y value that would make it true. So here's a list of easy numbers, put it that way, right? Nice integer values that are going to work real easy with this, times 3. And then I can do the calculation. I'll figure out what is the y value that goes with it. So if I put in a 0 for that x, 3 times 0 minus 1, I'm going to get y as a -1, right? 0 minus 1. So the ordered pair, the combination of x's and y's that makes it true is when x is 0, the y has to be a -1. So I can really just put parentheses around that. There's my ordered pair with parentheses, put a comma in the middle, right? Try it again. What if I put in a -1 for the x? What do I get? Here's my parenthesis around that negative sign, right? So -3 minus 1, minus and more minus a -4. So if x is -1, the y value that comes out, or that goes with it, is a -4. That would be another solution to this original equation. And we'll just keep going here. What if it was a 2? Y equals 3 times 2 minus 1. 6 minus 1, y equals 5. All right, finish it up here. What if it was a 3? 3 times 3 minus 1. I get y has to be an 8. So there are a bunch of ordered pairs. That would be solutions to that equation. Here's one in that other shape. All right, it's in that other shape. And again, we're going to see a table of values. Now here I'm going to sort of set you up. I think it's in section 4.3 where we're going to talk about graphing using the intercepts. The intercepts, that's a point that's on the axis. We call it an intercept. Almost like it should be intersect. Where does it intercept the axis? Well, if I say my x value is 0, it means somewhere I got a point somewhere on the y-axis. notice that if these two numbers, I'm sort of cheating, setting you up, right? If these two numbers divide nicely into that one over there, and you're going to see that most of the time in our practice problems here, putting in a 0 for one of them makes it real easy to find the other one. So problems are going to do that for you, I think, at this point. And here's a third point. Hopefully it doesn't get too messy, right? Well, not right now. They're not going to get messy on this. So in that first one I did a minute ago with that table, this shape works really well if you're given an X number. Stick in the X value and do all the work on the right side. Well, here you can pick an X or Y, and equally helpful or challenging. And so maybe you want to pick some nice numbers that make things work out nicely. Avoid the fractions, right? The zeros, like I said, are nice ones, and this problem is giving us that -5. I bet it works pretty well. So if X was a 0, here I go, 2 times 0 minus 5y equals 20. So that's a 0. Here's eventually I just kind of say, oh, if X is a 0, that one goes away. Right? Cover up math here. So I have minus -5y equals 20. If I divided both sides by the -5, I'd get a -4. Not showing too many steps there. I hope that makes sense. So if X is a 0, the Y has to be -4 to make that true. What if the Y was 0? That's what I was getting at here. We plugged in X's. Here we could plug in X's or Y's. If the Y was 0, that just cancels out, right? So I have 2x equals 20. Divide by the 2, I'd get X is a 10. So what did I have over here? Okay, so right there, here's ordered pairs I'm really building. 0, -4 is the solution, and 10, 0 is the solution. Now one more number they said, let's try. X is a -5. 2 times -5 minus 5y equals 20. -10 minus 5y. Right, that's going to work out to be a nice number. Right? Add the 10, -5y equals 30. Divide by the -5, and I get -6. I'm trusting you understand if I'd shown all the division and stuff like that, but you get it. All right, filled up that board. But there, they gave me a table of values, and I had to plug in those numbers to see what the corresponding variable value was that went with it. Finding solutions. Some of the problems eventually then are just going to ask you to find 3 solutions. Find 3 solutions yourself. Depending on what the shape of the equation is, to start with, you get to pick some numbers to put in. If it's in this shape, I've already kind of mentioned, it's usually very convenient to pick some nice X values, because then all your work is going to be over here. If you're just looking for any 3 solutions, pick some nice easy numbers. I usually like to pick a negative and a positive, and maybe even just a 0. But you can pick whatever numbers you think are going to work pretty nicely for you to plug in there. If X is a -1, I got a 6, huh? And so on. This now is, since I've decided which numbers I want to plug in and test, this is just like the previous examples. So some of them eventually will just ask you to pick your own numbers to plug in there and then find the corresponding Y values. There's going to be a lot of possibilities for those that could work. And if you've got one that looks like that shape. All right. Well, were they nice to you? Do the 4 and the 2 divide evenly into the 8? Oh, yes, they do. So that makes picking a 0 for an X or a 0 for a Y good, easy choices for coming up with nice number, not fraction answers. If you pick out some other number and it gets to be a fraction answer, it's a fraction answer. That's okay. You know, I could put in something like maybe 2. These are all multiples of 2. Maybe a 2 would work. You know. So again, if I put in a 0, I'd get 2y is 8, so y would be a 4. Or if I put a y was 0, 4x is 8, so x must be 2. If I put in the 2, let's see. Oh, it's going to be the 0. I just made it up, right? That's what that one turned out to be. Pick your own numbers and plug them in and then see what you get to go along with it. All right. Good. Let's see if I can. Let's get one here. Here's another one. All right. Pick 3 numbers. Maybe you'll figure out eventually here. No, 2 of them are going to be good enough. That is 2 solutions are going to tell us a whole lot. But I'm just going to pick my easy favorites right there. Plug them in. So if x is a -1, -2 minus 3, I get y has to be -5. Right. If x is a 0, that's going to be 0 minus 3, y will be a -3. And if x is a 1, y equals 2 minus 3, I get a -1. All right. These are 3 solutions to that equation. X's and y's that go together to make it true. If I put them on the graph, right? X is a -1, y is a -5. -1, 1, 2, 3, 4, 5. I do this nicely, neatly. Right? If x is 0, well, I'm right on that axis, y is a -3. If x is 1, y is -1. There are those 3 dots on that graph. You see a pattern? Linear for line. Those are 3 specific solutions to that original equation. If I see the pattern and I connect the dots. Here's where mom will ask you to do this. You have to grab the pencil and click one dot and click another dot, so it puts this line on the graph for you. If I connect the dots, they all are on a straight line. That's what's really special and unique about this situation we're dealing with now, these equations with 2 variables that are linear equations. Their pattern of the solutions creates a line, a consistent pattern that we can follow. Now, I calculated 3 specific solutions, but any point on that line is a solution. All right, would that work? 2 and 2. Well, no, my lines, my lines must be getting spread out or something. I have a hard time picking one that works there. But what was that? 2 and 2. Is that going to work? 4 minus 6. No. Oh. Well, guess it's supposed to be down here. Gee, make it look better. At any point on that line, that looks like 2 and 1. If I put that in, 2 for x, I get 4. Minus 3 gets me the 1, right? I put in that into my equation, that has to make it true. It's on that line, right? 4 minus 3, I got 1. Any point on this line, even the messy fractions in between, is a solution to that equation. An infinite number of possible solutions. All right. Now this is not quite the right looking graph. Maybe I'll just sketch something, right? Maybe here's my plumber equation, right? If he doesn't work anything, he's going to charge me 80 bucks. He showed up, and sorry, can help. He, she, whoever these days, right? But for every hour, it's going up. But it's going up at a steady rate, so I could calculate. Eventually, I can calculate how much it would cost me if the person has to work this long or that long, right? So this equation, this line models the situation. We can use it to predict future values or maybe previous values, like a time problem, something like that. How am I doing here? All right. I've actually started 4.2, all right? And I started actually putting them onto the graph and connecting the dots and making a line that was graphing linear equations. That's what 4.2 is going to ask you to do. 4.1 was all the basics about, you know, the graph grid, ordered pairs, positive negatives, and just practicing plotting points and then verifying solutions. 4.1. 4.2 is going to show you a bunch of different equations and ask you to find 2 or 3 solutions, plot the points, put 2 of them on the graph. Any 2 points, that's what I started to get at a minute ago. Any 2 points determine a line. You might have heard that somewhere before. I've got 2 points. There's only one straight line that can go through them. Right? Now, as soon as you get into the next level of math, you'll see relationships where sometimes it's not always a line, right? If I throw that ball off the roof, it goes up and then it comes down. There's an equation that describes that shape, right? Not all the relationships are linear. That's kind of what's special about linear. Or all this talk lately about flattening the curve. All right, well, if I start out with 2 people with the bug and they double because they came into contact with some other people, it's going up, and then those doubled people double again, come up with more and more people. This is what's called an exponential curve. It's multiplying like rabbits, double, 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 double. You know, it grows very quickly. That's what we're trying to flatten that rate. Eventually, unfortunately, it seems to be continuing to climb. Hopefully we find a vaccine soon. Just to get off track a little, but that's what all that talk about flattening the curve is. But we're going to deal with lines. Everything will be a straight line. If it's not a straight line, you did something wrong. Well, I've got a whole list, a page full of examples for 4.2. Everything's a little different, right? This one works better if you think about it this way, plug in this kind of number. So we're a little early, but why don't we stop there? That's all I really scheduled for today with the 4.1. And tomorrow we'll come back and we'll just look at a whole bunch of examples of equations and plugging in some points and drawing or graphing their lines. And you might be able, you know, it might make enough sense already that you could try some of the 4.2 if you wanted to. Okay, so I think I'll stop for today then, and we'll see you again tomorrow. There's all the, like I tried to mention just before our test, this is really kind of what the power of algebra are, these relationships. The final value I can calculate based on the relationship I know over there, you know, X's and Y's. And so everything we've been doing so far is building up to Now we can put two of them together and look for these patterns. More and more, higher level, you might say, algebra classes gets into more and more of those different graph shapes, and there are different equations that are used to describe those relationships. Okay, folks, well, see you tomorrow. And Tara, if you want to check in with me, or hopefully you saw my message that I sent you this morning, okay? But we can chat later here, okay? So see you later.
Okay.